In this video, we will learn how to calculate the accelerations of a planet, but when we use Earth as our example. At the same time, we will learn what happened to the gravitational accelerations at different spots of the Earth. Either we are inside the Earth, on the surface of the Earth, or we are on the way flying to the moon. And last but not least, before you go home, you will know the in and out of this beautiful graph. Let's begin with why all of us will be falling into the Earth no matter how high we climb. This is all due to every object that near to the Earth will eventually accelerate towards it, all thanks to our gravitational force. According to Newton's second law of motion, F is equals to ma. And according to the universal law of gravitation that we have learned in the previous video, F equal to gmm over r squared. In this video, we will use the capital letter M to represent the mass of a planet. But since we are using the Earth as our example, the capital letter M is referred to the mass of the Earth. We use a small letter m to represent the mass of an object. It can be any of the object, it can be a human or any stuff. So since both of the F represent the same gravitational force, we can put it together in one equation where ma equal to gmm over r squared. Since both of the m represent the mass of the object, we can cancel it out and bam! We have the formula for gravitational accelerations. And what's so special about this is we have discovered that the gravitational accelerations does not depend on the mass of the object. Means everybody on this Earth, no matter you are 5 kg baby, or you are 100 kg of big boy, or you are 1000 kg of the car, all of us will experience the same amount of gravitational accelerations. And since both g and m are also constant, it means our gravitational accelerations only will be affected by the distance from the center of the object to the center of the Earth. In fact, our gravitational accelerations will decrease with a factor of square distance when we are further away from the center of the Earth, which it makes sense because when we are further away from the planet, we experience a weaker gravitational force, hence a lower amount of gravitational accelerations. But these relations only apply when we are on the surface of the Earth or we are flying to the moon, means we are already away from the Earth. So by knowing these relations, we can derive a new formula, because if I were to times both sides with r squared, we will arrive at ar squared is eventually equals to 1, means 1 is a constant, so we can say ar squared is equals to constant. The good thing about this one is we can compare our initial and final state as long as we know the ar squared is a constant. So we can write down as a1r1 squared equals to a2r2 squared, where 1 represents the initial state and 2 means the final state. What it means is, let's say in the beginning, I'm on the surface of the Earth. I will experience a gravitational acceleration of a1. But this is when I'm r1 away from the center of the Earth. Maybe one day, I decide to explore to the moon. So now, I'm at r2 away from the Earth and I will experience a gravitational acceleration of a2. So in the beginning, I'm on the surface, and in the end, I'm on the way to the moon. So this is what I mean by initial and final state. By using this formula, we were able to solve a lot of the problems. If I were to rearrange this formula so that all of the a's will go to the left and r go to the right, so a2 go there, we can divide, so we have a1 over a2 is equals to whatever r is on the right, so we have r2, r1 coming here is become divide, so r2 squared over r1 squared. So we will use these relations to solve a lot of the problem in this video along with some of the constants that you can find on your formula list. Let's begin with finding out what is the gravitational accelerations when we are on the surface of the Earth. As we have learned in the last video, whenever we are on the surface of the Earth, we are actually r distance away. R is the radius of the Earth. So we use the formula of A equal to gm over r squared. By substitute all the value, g is the universal constant, m is the mass of the Earth, and r is the distance from the center of the Earth, while we are r distance away, which is the radius of the Earth. And by pressing the calculators, we get the answer of 9.81 meter per second square. And this boy dreamed to become an astronaut. He wants to know what happened to our gravitational accelerations when he is 2r, 3r, and 4r away from the center of the Earth. Let's figure out what happened to our gravitational accelerations when we are 2r away from the center of the Earth. We can use these relations to derive the relations. So you can imagine now in the beginning, when we are at r1 means initial distance away from the Earth is r, and we experience the gravitational acceleration of 9.81, or I will use A for this example. Means A is just the 9.81, I wouldn't need to keep on writing down the numbers. And at the final state, R2, I'm at 2r away, and what happened to my accelerations? So I want to find out my gravitational acceleration. This is what I want to find out. I have my A1 is A, I have the R1 is R, R2 is 2R. So let's find it out together. So we have A2 over A1 equals to R1 is our R, and our R2, which is our final state, is actually 2R away. The common mistake is whenever the student want to expand the bracket, they forget to square the number as well. Don't forget to square the number. So that we have R squared over 4R squared, which is A2 over A1. And we can simplify the R square. So now we left with 1 over 4 is equal to A2 over A1. If I were to move the A1 to the right hand side, I will have A2 equals to 1 over 4A1. So this means that when we are at the distance of 2r away from the center of the Earth, we will experience only 1/4 of the initial accelerations when we are on the surface of the Earth. So now you can take your time to find out what happens when we are 3r away from the Earth by using the same formula, where now we are at a distance of 3r. I want to figure out what happened to the gravitational accelerations. So we are looking A3. So A3 as compared to A1, the R1 initially we are at r meter away, but now in the final state, we are at the 3r away from the Earth. Again, when we expand this one, this is supposed to be the 9r squared. Please square both the number and the alphabet. So r squared cut off, we have 1 over 9 A1. So it means when we are at 3r away, we only experience 1 over 9 of the initial accelerations. As you can guess, when we are at 4r away from the center of the Earth, we will experience only 1 over 16 of the gravitational accelerations. So as we can see, the gravitational accelerations eventually decreases with a factor of square the distance away from the Earth. So this again only apply when we are on the surface of the Earth, or we are already on the way to the moon or away from our Earth. So now we're going to discover what happens to the gravitational accelerations when some of the the Earth digger decides to dig into the Earth. When she arrives in the inner part of the Earth, what happened here is, you can imagine now, this girl is stepping on to a smaller kind or the smaller version of our Earth, where the blue color region here is now no longer exert a net gravitational force on her, means the outer portion of the Earth is no longer exert the gravitational force on her. In fact, they do still exert the force, but it will cancel out eventually. But for a simplicity in these explanations for this video, we just assume that now she is stepping on top of a smaller version of our Earth. So this green portion is the only part that's still exerting a net gravitational force on her. But since we know in the last video, the gravitational force is directly proportional to the mass of the object. As a result, the smaller mass of the sphere would only exert a smaller gravitational force on her. Therefore, the gravitational acceleration will be decreases. And this theory only correct when we assume the Earth has a uniform density. It means no matter where are you inside the Earth, all over the Earth has the same density. And we also assume Earth is a perfect square. As we know, density has the formula of mass over volume. And sphere has the volume of 4 over 3 pi r cubed. So if I were to find the mass of the Earth, I can say the mass of the Earth will be equals to the density of the Earth times the volume of the Earth. But we know volume of the Earth is just 4 over 3 pi r cubed. So we can say the mass is eventually equals to 4 over 3 pi rho r cubed. So this is why we have something like this once we expand the bracket. But if we want to find the gravitational accelerations, we have the formula of gm over r squared, where the capital letter M is just the mass of the Earth. So we can substitute in by g prime, which is the gravitational acceleration inside the Earth, is equals to g bracket 4 over 3 pi rho r cubed over r squared. And we can simplify the r squared with r cubed. Now we will left with only g prime equals to g, the 4 over 3 I carry it into the front, pi, and then we have the rho and r. So from here, what we can see is the pi is a constant, the g is the gravitational constant, the density we assume to be the same means it's also a constant. So the gravitational accelerations now is directly proportional to the distance from the center of the Earth. It makes sense because it means when we are further away from the center of the Earth, we experience a higher gravitational accelerations as we are eventually stepping on a bigger version of the Earth as compared to the previous version of it. So it means when we are on the yellow circle, the yellow sphere is actually bigger than the green color one. This is why when we are away from the center of the Earth, the Earth become bigger and bigger. It will exert a higher gravitational force on you. Hence, you have a higher gravitational accelerations. So this relation is a directly proportional. Again, this only happens when you are inside the Earth. This is due to only the mass of the inner smaller sphere will have the net gravitational force on you. And by derive the formula, indeed, this relation is a directly proportional. But this changes whenever we are on the surface of the Earth or beyond the surface of the Earth, especially when we are on the way to the Moon or to the Mars. This happens because the entire mass of the Earth will eventually exert a gravitational force on Earth or satellite. And we have discovered the formula and the relationship with what happens when we are away from the surface of the Earth. It decreases with the factor of r squared. As promised, we will go home with learning how to plot the graph. So we're going to use the x-axis to show the distance from the center of the Earth and the y-axis to tell us what is the gravitational acceleration on that particular spot. So we will start with the center of the Earth and check what happens when we are at the R away, which is the surface of the Earth, where we are 2R, which is on the way to the moon, 3R, 4R, and also 5R. Again, as a reminder, when we are R away means we are on the surface of the Earth. To know what is the gravitational acceleration on a particular spot, we can use the formula that we have learned, which is gm over r squared. As we have done just now, when we are on the surface, is about 9.81. When we are 2r away, is only 1/4, 1 over 9, 1 over 16, and 1 over 25, because they decreases with a factor of square. And one more thing to know, when we arrive at the center of the Earth, this is the place where you experience zero gravitational force. Hence, you will have zero gravitational accelerations. You can think of like you are symmetrical because this is a perfect sphere. If we exert all over the directions where it will cancel out each other, therefore you experience no force at all. And when we are on the surface of the Earth, this is where you experience the maximum gravitational accelerations. So this is eventually same as 9.81, which we have calculated in the beginning of the video. And when we are at 2r away, we need to experience 1 over 4 g. And when we are at 3r, we are about 1 over 9. When we are at 4r is 1 over 16, and 5r is 1 over 25. So again, when we are inside the Earth, the relation is eventually a directly proportional kind of relations. When we are further away from the center of the Earth, the stronger is the gravitational accelerations. But it changes whenever we arrive at the surface of the Earth or beyond the surface of the Earth, where it decreases with a factor of r squared. Hence, we have this curve that going down. So this is a very important piece of information where you will need to remember that when we are inside the Earth, which is below the surface of the Earth, this relation is a directly proportional. Once we arrive or beyond it, this one becomes the inversely proportional to the square distance from the Earth. And as a bonus, we're going to find out what is the gravitational accelerations by using the numbers. So if the boy is on the surface of the Earth, it means we are only r distance away. So by plugging in the values as we have done before, it's going to be 9.81. But what happens now if we have the satellite that is about 1,000 kilometers away from the surface of the Earth? So this is where we need to take account of the distance from the surface. You can imagine now, this is the perfect sphere for our Earth. Usually we say we are r distance away if we are on the surface. But satellite is flying on top of the sky. So we need to take account the additional 1,000 kilometers away from the surface of the Earth. So in total, the distance from the center of the Earth is going to be the radius plus the 1,000 kilometers from the surface of the Earth. So the 1,000 kilometers will convert to become the SI unit, which is meters. So kilometer to meters times 1,000. This is why we times 10 to the power of 3. So by doing this way, we can just plug in all the constants and we get the gravitational acceleration of 7.33. Trust me, you must press the calculator by yourself so that you will get your muscle memory works on this kind of questions. It seems to be very easy, but this is the part where you will mess up most of the times. And last but not least, what happens when we have a rocket that is 2,000 kilometers away from the surface of the Earth? Again, you need to take account it's not only the radius of the Earth, but they are also 2,000 kilometers away from the surface. So the actual distance is going to be the radius of the Earth plus the 2 million meters, because 2,000 kilometers is 2 million meters away. So by plugging in the values, we get 5.68 meter per second square. So in conclusions, in fact, when we are on the surface or beyond the surface of the Earth, the gravitational acceleration of the Earth eventually decreases with distance. Hey, if you want to join my online tuition class, please drop me a message on Telegrams. Or if you want to support us so that we can make more videos like this, the simplest way is just to sharing the video with your friends. Hit the like buttons and consider subscribe to this channel. See you in the next video.